Welcome to the Crazy Hat Chemist, so another video on solutions. And how have I got a solution for you? Well, one of them is that this is the last video of this unit. So that's a great solution. Bam! So today we're talking about osmosis and osmotic pressure. Okay, the diffusion of solvent molecules through a semi-permeable membrane to a region of high solute concentration is called osmosis, when the molecule is water. Okay, an isotonic solution is one in which the concentration of ions is the same on both sides of the semi-permeable membrane, with no net movement of water, yielding equal osmotic pressure. That is, the water molecules do move back and forth, but no net movement of water. Okay, so here's some red blood cells here in this picture here. So I'm going to show an isotonic solution. That is movement of water into the cell, movement of water out of the cell. Notice the arrows are of the same length and magnitude. Okay, a hypertonic solution is one in which the concentration of ions is greater on the outside of the semi-permeable membrane as opposed to the inside, which has a lower concentration of ions, with a net movement of water out towards the greater concentration of ions, yielding a shrinkage of the cell. So here's an example of this. Notice that I have a very short arrow here. That means that water is coming into the cell, and yet most of the water is going out of the cell, and that will shrink the cell itself. Okay? The next one is a hypotonic solution. Okay, and a hypotonic solution is one in which the concentration of ions is lower on the outside of the semi-permeable membrane, as opposed to inside, which has a higher concentration of ions and a net movement of water inside towards the greater concentration of ions, yielding an expansion or a ballooning effect of that cell. So notice that there's a great number of water molecules moving into this cell and very few water molecules moving out of that cell, and therefore it expands. Okay? So hypertonic, so you're hyperactive, you have a lot of ions, greater concentration of ions. Hypotonic is underactive. Hopefully that makes sense for you. Okay? Reverse osmosis is an application of external pressure to force water from a high solute concentration to a low solute concentration. That yields relatively pure water. And here's a reverse osmosis system that I have underneath my sink here. That big gigantic tank there holds the water, but all those filters on the right hand side, okay, that's the reverse osmosis system. So it's building pressure to push the water out through that semi-permeable membrane in the reverse direction against the high concentration of ions. And then the high concentration of ions stays inside the filtration system, yielding relatively pure water on the other side. Okay, sterile saline for injection, USP, is isotonic for humans to help prevent us from increasing or decreasing in mass significantly. So in the title of this slide, I have a bag to the left. That is a sterile saline for injection for USP, and you can see that in hospitals. Okay, so if you ever get an intravenous injection of any kind that has a bag that has, and hopefully you've seen this at hospitals or maybe in a movie or something like that. If you have an IV fluids or something like that, that needs to have the same salinity concentration as the human body as well as the pH. Otherwise, we would go into serious shock because of our cells would lose lots of water or gain lots of water, and that's never a good thing, and our ion concentration would be way off, and that is a bad thing for our heart. Okay, so this is a picture of reverse osmosis and osmosis. Notice on the left-hand side with osmosis, the red arrow is showing the net movement of water from a low concentration to a high concentration of ions, and then you can see on the very top of that, where it's not equal in water level, the osmotic pressure. Okay? Reverse osmosis is applying pressure to that high concentration of ions to force the water through that semi-permeable membrane to the area where there are fewer ions. All right, hopefully that little diagram and picture described osmosis and reverse osmosis. Let's go on to this next one, which is osmotic pressure. Osmotic pressure counterbalances the pressure of solvent molecules moving through a semi-permeable membrane. And this is the equation for this. Okay, it's pi equals I CRT. Now, pi is not 3.14, okay, but it is just, that's the osmotic pressure right there. I is the Van 't Hoff factor. We've discussed that already before. C is the concentration, and this time the concentration is going to be in moles per liter, which is molarity and not molality. R is the gas constant. T is the temperature associated with this. So here's our question. It's in the lower left-hand corner here. We're going to calculate the molar mass of hemoglobin if 35.0 grams of hemoglobin is added to 1 liter of solution. The osmotic pressure is measured to be 10.0 millimeters of mercury at 25 degrees Celsius. There is a little diagrammatic three-dimensional drawing of hemoglobin. I've drawn that for you. We're going to calculate the molar mass. Now, the molar mass is grams per mole. Hopefully you remember that from way back in the early part of chemistry here. So do I have a mass? I certainly do. I have the mass, and that is the 35 grams. I just don't have the moles. So I need to solve for the moles that I'm going to plug into this equation to solve for the molar mass of hemoglobin. So using the osmotic pressure and the temperature and the 1 liter of solution, I will be able to solve for the moles of the hemoglobin, and then I will solve then subsequently for the molar mass. So I've rearranged the osmotic pressure equation to solve for concentration, which is moles per liter. Okay, and how many liters of solution do I have? 1 liter of solution. So I'm going to essentially solve for moles. Pi is the osmotic pressure. I need that to be in the right set of units, and that is dependent on the R value, which is the gas constant. I is the Van 't Hoff factor, and that's going to be in relation to the solute, which is hemoglobin. And hemoglobin has a, you should think about what the I for hemoglobin is. So the pi, the osmotic pressure here, is I'm going to take the 10 millimeters of mercury, and I'm going to convert this into atmospheres with this unit conversion. Okay? And that's going to go right there in the numerator term. The Van 't Hoff factor for hemoglobin is 1 because it's a molecule, it is not an ionic compound, and that is going to go right there. Then I have the gas constant and I have the temperature. I've converted my 25 degrees Celsius into Kelvin, that's by adding 273.15. Okay, I have the value of I, that's 1, the 0.0821 liters atmospheres moles Kelvin. Okay, that way it allows me to cancel out the kelvins, cancel out the atmospheres, and I'm going to have moles per liter, which is a concentration, and that's the C, which is the molarity. So I'm going to solve for the concentration, which is moles per liter, and remember I have a 1 liter solution, so this is 5.40 times 10 to the negative 4 moles per 1 liter. So how many moles do I have? 5.40 times 10 to the negative 4 moles. I'm going to plug that into that molar mass equation there at the bottom. So I got 35 grams, that's the amount of hemoglobin I have, divided by the moles of hemoglobin here from my osmotic pressure calculation. And I'm going to have this number here, which is 64,900 grams per mole. Now, since this is a protein, and I'm a biochemist, truly, since this is a protein, we use proteins. We use a different set of units besides grams per mole if we are talking about proteins. And those are daltons or kilodaltons. And since this is a large number, I'm going to convert this to kilodaltons, which is 64.9 kilodaltons. Okay, it's the same thing as kilograms per mole. All right, that's osmosis and osmotic pressure. I have one more thing here for you. Okay, this is from Mr. Albert Einstein, and of course, he's a smart guy, so you should listen to his advice. Learn from yesterday, live for today, hope for tomorrow. The important thing is not to stop questioning. Great quote. I want you to apply that to your life. I am the Crazy Hat Chemist. I got a Crazy Hat video here for you. This was a crazy unit. This is a crazy hat. I love this hat. Super cool. Try to figure out what anime character it's coming from. That's your question. If you love this video, give me a thumbs up. Subscribe to my YouTube channel. Pass on my YouTube channel to all anybody, your cool chemistry friends, people that aren't cool chemistry friends but will be cool chemistry friends after they watch my videos. I will see you next time for the next unit. Bye for now.